Hi. As I mentioned in our previous video, when we were discussing integrals thus far, we were actually discussing indefinite integrals. Look, what do I mean by indefinite integral in this context? Look, if we calculate an integral, indefinite integral, as a result, we are getting a function, primitive function, plus an arbitrary constant c. So look, what we are getting over here is actually a function, right? So what we get over here is a function. But, as we said before, integrals have some very specific interpretations in terms of mathematics and with its applications to economics, finance, or management. But let me illustrate this point on what we already know. And what we already know are derivatives. Look, for example, if I have a function y equals f of x, then the derivative of this function is going to be either dy dx or f prime of x. And look, what do I have over here? Here I have a function that we call primitive function. And what do I have over here? Here I have another function, right? I have derivative function or direct function. And look, exactly the same as over here. Just the order has been reversed. Because here I have derivative function and over here I'm getting primitive function. And look, we said before that derivative measures the slope of a function at a given point. And look, let's do it with a very simple example. Let's just say that y is x is some function of x and it's equal to x squared. Now, if I'm calculating the derivative of this function, so f prime of x, I'm getting that this is equal to x. This is a derived function. So, this function that we see over here is actually showing us slope of this function at any point. But look, at this moment, if you're gonna ask me, so what is the slope of x squared at 1? I don't know it yet, right? What I need to do is to substitute the value inside the derivative, right? So now, if I'm going to put inside the derivative 1, I'm going to get that this is 2 times 1, which is equal to 2. So, we get from this that the slope of y equals x squared at 1 is equal to 2. And look, simply by putting different values of x inside the derivative, we are learning what is the slope of x squared in this case, so of the primitive function at any given point. So look, this is how we get the point, the slope of the function at any given point. Of course, this procedure is very convenient to us. Why? Because once we've calculated the derivative, knowing which points interest us, we can easily find it. Look, this is exactly the property we were using when we were finding maximum and minimum. And look, Now, we've actually, what we did, do start with integrals, is this part. We defined and we learned maybe how to calculate integrals, just like we learned how to calculate derivatives, and we learned different rules that are allowing us to do it, right? So basically, what we are getting over here is that we are transforming one function into some other function that is giving us some information, this time, about derivative function. Okay, and look, today we are going to move one step ahead. Look, here we call them indefinite integrals because they were containing x inside. And because they were containing x, we were stuck at this point. We know that this is a primitive function that gave this derivative function, but we still cannot really tell what does it supposed to mean. And to get to this point, we need definite integrals. And look, here we will have more or less formal definition of definite integrals. So, look, let's go through it step by step. For indefinite integral, so integral f of x dx, which is equal to capital F of x plus arbitrary constant. If we choose two values of x in the domain, so we are simply choosing the two variables that we can plug in to these functions, and those we will be calling a and b. They have specific names, but I'm gonna get to this a little bit later. A and b, where a is lower than b. It doesn't need to be the case always. We will actually discuss what is happening if we reverse their order, but let's stick with this for now and substitute them in the following way. So look, what we're going to do is that we are calculating indefinite integral f capital F of x plus c. And look, what I'm going to do first is inside this function, I'm substituting b, and I'm getting this expression. And then from this expression, I'm taking this expression again, I'm substituting a, and I'm subtracting. And look, out of this, I'm getting f of b plus c minus f of a minus c, which tells us right away that the two c's must be cancelling each other out. And then we are getting this expression, right? F of b minus f of a. And look, if we will calculate it in this precise way, we will obtain numerical value. So we will get expression without any x or an arbitrary or an arbitrary constant. Okay, so this is giving us something that we will be able to use a little bit later for interpretation. Just what is the key over here is that in this setting, so in the setting line over here, f of b minus f of a is a definite integral in this specific interval from a to b. Okay, so basically what we are going to start doing now is we're going to move from this step to this step. So now we're going to be getting closer and closer to establishing what actually an integral is giving to us. an integral is given to us. Okay, let's summarize. If we have now definite integral, we write it as integral from a to b out of f of x dx, where? Now, look, this a that you see over here is the beginning of this interval AB, and we call it lower limit of integration. The B that we have on the top is is of course, as you might expect at this moment, called upper limit of integration. Okay, and look, how do we calculate definite integral? Look, first thing we need to do, of course, is to calculate indefinite integral. So we will get here f of x. And look, very nice thing with definite integrals is that, look, the c's are canceling each other out. So we no longer need to add c at the very end. But what we are adding here is this half bracket, let's call it like that, and here we're gonna put b and a. And look, in the last step, what we are going to do is to substitute b inside f of x, write it here, and then from this we're gonna subtract f of a. And look, the outcome of this is going to be a numerical value, a number. And this number will have a very, very meaningful interpretation. But okay, before we're going to get to what this interpretation is, let's for a while practice just calculating definite integrals. As you might expect, we are not going to fall too far from what we already learned. The only new thing is going to be substitution with specific values. Plus, one additional thing when it comes to integration by substitution. Okay, so our first example is integral from 1 to 5 out of 3 x squared dx. So look, first thing I need to do is to calculate definite integral. So this is going to be just x, indefinite integral. So this is going to be x cubed. And I'm putting 5 and 1 here. What am I doing next? I'm substituting first 5 instead of x, and I'm subtracting, and I substitute 1 instead of x. So I'm getting that this is 125 minus 1, which is 124. Okay, so let's get to the next case. Now we have integral from a to b, k e to the power of x dx, where of course k is a constant. So what is going to be a indefinite integral of k times e to the power of x? This is of course k e to the power of x. Then we put a and b over here. Then of course we substitute those, so we get this is k e to the power of b minus k e to the power of a, right? And we get out of this that this is k times e to the power of b minus e to the power of a. So we got 0, 4, and we've got inside 1 over 1 plus x plus 2x dx. Okay, again we need to start by calculating indefinite integral. So, what we see over here is that derivative of the denominator is 1, which is what we have in the numerator. Now, so, indefinite integral of this is 1, is ln 1 plus x. Now the question is, do we need to impose absolute value? In this case, no. Why? Because look, here we are starting at 0, right? We're finishing at 4. Here, I just need to calculate ln from 1 plus x, so 1 plus 0, ln 1. It can be calculated, so in this case, I don't need to include here any negative values, so I cannot get negative values, we don't need absolute value here. Okay, and then plus 2x, which transforms into x squared. And I put 0 and 4 here. So, first I substitute 4 instead of x. I'm getting that this is ln 5 plus 16, right? Then minus ln 1, right? Because now I'm substituting 0, minus 0 squared, right? So, because ln 1 is equal to 0, our outcome is simply ln 5 plus 16. Okay, so let's just try one more, and then we can move to interpretation of definite integrals. Okay. We've got integral of from 1 to 2 out of 2x to the power of 3 minus 1 squared times 6x squared dx. Okay, and look, here the situation starts to become a little bit more complex. First, in order to solve this one, even just to find indefinite integral, what we need to do is, of course, to use integration by substitution. What is the problematic term? Well, problematic term is the one we've got over here. So, we choose our u to be 2x cubed minus 1. And look, in this case, u dx, so derivative of u with respect to x, is 6x squared. Right? So, what do we do next? Well, now we can start substituting. We get here from 1 to 2. Here we have u squared du dx dx. Right? So, those two cancel each other out, and we are getting u squared du. Okay. And actually, there is another thing we need to take care of. Look, as you might notice, I haven't put here limits of integration. I did put it here, but was it justifiable? Look, what has happened over here? This is no longer a function of u. So, a function of x. This is a function of u. What does it mean is that now limits of integration needs to be adjusted accordingly. So how do we do it? Look, first, limit of integration a. When x was, when we were talking about variable x, right? Limit of integration at a was 1. But now look, if we are going from x to u, what does it mean? Look, it means that now u is the function we are taking care of. So look, because u is equal to 2x to the power of 3 minus 1, then what I need to do is to substitute this x over here. And then I'm obtaining, maybe without this, I'm substituting it over here, and I'm getting that this is 2 times 1 to the power of 3 minus 1, which is equal to 1. Well, as you might notice, this time it didn't make much of a difference. We still have 1 over here, 1 over here. But what about b? b was given, for x was equal to 2. So what is going to be a situation when we turn from x to u? Well, when x is 2, u, which is equal to 2x to the cube minus 1, turns into 2 times 2 to the power of 3 minus 1, which is 16 minus 1, which is 15. And look, now, you see over here, what we did was to we changed the limits, of integration. Okay, so now we can move on to calculating it. We're getting that this is u cubed over 3, 150. So the only thing left is the substitution of the new limits of integration. So again, that this is 15 to the power of 3 divided by 3 minus 1 to the power of 3 over 3, which after various calculations is going to give us 1,224 and 2/3. Let me just check. It's yes, exactly. So look, now we know counterpart of putting x, specific value of x in case of derivatives. We know how to do it now in case of integrals. But look at the difference. The difference is that when we were calculating derivatives at a specific point, all we had to do is to calculate derivative and put the specific point inside. In case of integrals, it looks a little bit different. Look, we actually need to have 2 points to calculate definite integral. And this is not a coincidence, because what integrals are allowing us to do is to calculate an area below the function. How it is done, we're going to learn in the next video. Thank you for your attention.